Hey my dear students, welcome back. In this video we are going to learn reaction of carbohydrates. They are so similar with what we have seen previously, just we have to apply to this big structure. For example, we have to convert the aldehydes to alcohols or carboxylic acids, the same reagents with some small changes. We are going to do also change lengthening and change shortening to the carbohydrates, right? And we are going to deal a little bit with disaccharides, when they are reducing sugars and when they are non-reducing sugars, and give they reactions or no. Without any further ado, let's dive into it. First, we are going to do conversion of carbohydrates into esters, right? What do we have here? Alpha-D-glucopyranose. We treat that with an acetic anhydride in pyridine, 0 degrees Celsius. All those positions are going to be filled with the ester groups. So what we are going to have, ester groups, right? If we simplify things, write this in a short way, like AC, we are going to have acetylamines, right? This is the ester from the carbohydrate monosaccharides. Let's move further. We can convert carbohydrates into ethers. How we can do that? We react all those alkyl groups through a primary alkyl halide with not a strong base, with a mild base such as silver oxide. Is Williamson synthesis for ethers, but here we do not use a strong base but a weak base such as silver oxide to get the job done. Okay, what we are going to have here? So what we are going to have here, ether formation. We have to respect the position of this sugar, right? We cannot change them. Equatorial to equatorial, axial to axial. In case you want to add a name for this one, is beta-D-monopyranose. Pentamethyl ether, right? Now, glycoside formation. OC is replaced with O-side, which means that the reaction happens only in anomeric side. So anomeric side is this one here, right? If you are not clear what is anomeric side, check this previous video. It's important to understand this fully. If we react beta-D-monopyranose with methanol in presence of hydrochloric acid, you are going to have only the reaction on this side here. So the other parts remain intact. But the problem is that the reaction happens in the anomeric side and the products are in alpha and beta. Both products are formed. So first product is going to be this one. And the other product is going to be this one. The others remain intact. This is the beta one and this is the alpha one. Right? So to understand what is beta, what is alpha, I still again recommend to watch this previous video about the carbohydrates. So what would be the name for this one? Is going to be methyl beta-D-monopyranoside. Right? For this one here, methyl alpha-D-monopyranoside. Right? Let's move further. Reduction of monosaccharides to alditols. What is going to happen here? For example, beta-D-monopyranose, part of this equilibrium is going to be reduced and the equilibrium is going to shift to the right until the entire sugar is reduced. How do we reduce that? We are going to reduce here only the aldehyde group, right, with sodium borohydrate. And if we convert with sodium borohydrate aldehydes to alcohols, right? And the other parts remain intact. The name D-mannitol, right? Let's move further. Oxidation of monosaccharides to aldonic acids. So what is going to happen on this side? You are going to oxidize this aldehyde group to carboxylic acid with bromine in presence of water and pH 6. Right? And the other parts remain the same. So it's going to be L-gluconic acid. Right? Let's move further. We can oxidize to aldaric acid also. In this case, you oxidize this aldehyde group here, but also this alcohol at the end. Right? Both of them are converted to carboxylic acids. The body remains intact. It is done by nitric acid in the presence of heat, right? Now, in terms of naming here, is aldaric acid, L-glucose is gonna be L-glucaric acid. Right? Do we have any possibility to convert this alcohol to the carboxylic acid and remain this aldehyde intact? No. Only through enzymes. Through chemical reagents is not possible. Right? Okay, let's move now to Kiliani-Fischer synthesis. So in this way, we add one carbon more to the chain of the carbohydrate. So how we do that? We take, for example, a D-ribose or any other sugar you want. You treat with cyanic acid, and the second step is with hydrogen in palladium catalyst, and third step is hydrolysis. You're going to yield two alcohols that are epimer in the C2, right? Because first hydrox is going to be on this side, then second is going to be on this side, the allose and the altrose. How this happens? Through mechanism. We start from the aldehyde, we form cyanohydrine. Once we form cyanohydrine here, this one that is an aldehyde group is going to be converted to the OH, right? And this OH can stay on this side or on this other side. That's why you have two different types of sugars, epimer and C2, the new ones. So after that, with hydrogen in palladium catalyst, what you do, you convert them to imine. And after that, with hydrolysis of imine, you convert again the imine to the aldehyde group, but with the addition of one carbon, right? Let's move further. We have also the reverse, Wolh degradation chain shortening. What this does, it reacts, for example, D-glucose with hydroxylamine, form an oxime, and after that treat this with acetic anhydride. What it does, it forms a cyanohydrine, and with a base we remove the cyanohydrine, and this group here is going to be converted to aldehyde, right? And this is the final product, that is shortening, plus HCN, dearabinose, right? Let's move further. Disaccharides. We have 1,4 linkage that mostly are reducing sugars. For example, cellobinose, 1,4 beta glucoside. If it's 1,4 linked, it's a reducing sugar. Why? Because the anomeric OH is free to react or to be reduced, right? So it blocks for example, in this case, the beta hydroxy here, but it does not block this one here. Disaccharides can give the same reaction that we mentioned above if they are reducing sugar. So what we have here, for example, with sodium biohydrate, to reduce it, because from the name reducing sugar, right, you're going to open the chain here, and the aldehyde that is formed here is going to be converted to an alcohol. What about if we treat that with bromine in presence of water, an oxidation that we convert them to carboxylic acid, reducing sugars? Be careful, we are not talking yet for the non-reducing sugars. And if we do esterification of this sugar, yes, it is possible. You can do all those OAC esterification. AC represent acetyl. Sucrose is a typical sugar that is non-reducing sugar, and the linkage is 1,2. Glycoside linked. 1,2 means that both those are anomeric sites that are linked, so this sugar is not possible to be reduced. Right? Keep in mind those things. And that's it. No need for more. Thank you so much for watching. And with this video we close the carbohydrates and look forward to see you in the next video. Up until there, peace.